Good afternoon, everyone. My name is Zihao from Shanghai Jiao Tong University, and I'm honored to be here to introduce our work on supervised hashing. Supervised hashing is to learn compact binary codes of the training data to preserve semantic similarities. If 2 points are semantically similar, the Hamming distance between them should be low, and vice versa. In this example, the latter 2 images both contain people, but the former do not. Hence, the binary code of the first image is quite different from the other 2. Many supervised hashing methods optimize a form of loss function with a regularization term, which can be viewed as a MAP estimation of the hashing codes, just like these 3. However, these approaches are prone to overfitting unless hyperparameters are tuned carefully. So we turn to Bayesian methods in hope of solving this problem. Our model has a hierarchical structure. The likelihood is similar to that of latent factor hashing, but for the prior, instead of a single shared hyperparameter, we introduce a separate hyperparameter gamma k for each column of U. This formulation, therefore, is equivalent to automatic relevance determination. During inference, if some gamma k assumes large value, then the posterior distribution over corresponding column will be concentrated at 0, which means that the kth hashing bit is relatively inessential. Since exact Bayesian inference for logistic regression is intractable, we adopt mean field variational inference to tackle the model. The sigmoid function has a tight bound by local variational methods. However, consider the diagonal elements in S. The posterior over corresponding rule of U has a quartic exponential form, which is also hard to tackle. So we introduce a latent matrix V and replace the inner product of Ui and Uj with that of Ui and Vj. If we force the sufficient statistics of V be equal to that of U, then the approximation could be reasonable. Here are the MAP results of our proposed method and other baselines evaluated by several datasets. Our proposed BSH can tune hyperparameters automatically, therefore has better generalization ability and yields better accuracy than state-of-the-art. This picture shows the utility of ARD hyperparameters gamma. The experiment is conducted as follows. We learn a 64-bit length hash function and simply select k-bit codes according to the indexes of the k-smallest hyperparameters in gamma. The MAP of this method is compared with the MAP of the k-bit binary codes learning using BSH directly. We choose k equals 248 until 64 in actual experiments. From the picture, we can see the MAP curve of selected bits. The yellow curve is concave and close to the sine curve on 3 datasets consistently, which means that the hashing bits being selected earlier are indeed more discriminating. That's all. Thanks for listening.